Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, part 27. In this episode, we're going to talk about how we can apply SVM to multiple class classification. And then we'll discuss the pros and cons of this machine learning algorithm. And finally, we're going to conclude with its application in finance. Okay, so let's dig into it. This episode, part 27, is our last stop in our exciting journey of support vector machines. So if you haven't watched the previous videos, I highly encourage you to first watch them and then hop on board. Okay, so let's start with K multiple class classification problem using SVM. So remember, SVM by construction is designed to handle two-class classification, because if you go back to the definition of hyperplane, a hyperplane is something that separates the space, the ambient space, the surrounding space, into two subspaces. So by definition, it is used for two-class classification. What if we have more than two class? What if we have three-class classification problem, right? Like in this example, we have three classes of green, blue, red. Right, so how can we handle these questions? So there are two general methods to do that. The first one is called OVA, one versus all, and the second one is going to be OVO, one versus one. But before going over the details of these methods, I want to make sure that we understand how these F hats are calculated and what are they. So let me show you a very simple example here. Imagine in two dimension we are dealing with two-class classification, and there are, let's say, a bunch of red observations there and maybe some blue observations here. Okay, and I'm gonna call this one my red hyperplane. So let's call it red hyperplane. The reason that I'm going to call it red, because the way that we're going to look at this hyperplane is that if something is classified as red, call it 1, otherwise 0, right? So this is my red hyperplane. And this hyperplane has a functional form. Let's call it f hat. And I'm going to call it f hat, let's say red. Okay. And in part 23, we saw how we can calculate the perpendicular distance from a line, from a hyperplane. So for example, what is the perpendicular distance of this observation from the line? What is the perpendicular distance of this observation on the line, right? And in part 24, when we were talking about the optimization problem in SVM, we said that anything on the correct side of the hyperplane, we can assign them by +1. Anything on the wrong side of the hyperplane, we can assign them by -1, right? Now, if we multiply this perpendicular distance with the sign of +1 and -1, then that's basically what the f hat is going to tell us, right? So let me give you an example. Imagine for this observation, let's say the perpendicular distance, I'm just making up some numbers, is number 3, and I multiplied by the +1 because it's on the correct side of the hyperplane. So I'll get +3 for this observation. And for this one, let's say the perpendicular distance is 1. I multiply it by +1. So what I get for f hats for this observation is +1, right? But if I haven't, I don't know, maybe if I'm looking at this observation here, if the model calls it red, well, let's look at the perpendicular distance first. Let's say that the magnitude of the distance is in the order of 2.5. And if I multiply it by the negative sign, so what do I get? So I get -2.5. This means that this observation is on the wrong side of the red hyperplane, and the magnitude is 2.5. Okay. Now with that, let's see what is one versus all and how it's helping us to classify more than two classes, right? So here is our question. 3 classes: green triangle, blue circle, and red cross. Step number 1, we fit k different two classes SVM classifier, right? So k here in this case is 3. We're going to fit 3 different two-class classification problem using SVM, and we're going to call them f hat of kx, right? Each class versus the rest. So this is our step number one. So we're going to say that, okay, green versus everything else. Number two, blue versus everything else. And here, red versus everything else, right? If you only focus on colors here, green versus, so at the very top, green versus everything else, can you come up with the, let's say, hyperplane? Maybe, let me show it actually with green. Maybe this is our hyperplane, right? So let me try to use a straight line. So maybe this is our hyperplane, and I'm going to call it f hat green. So let's call it f hat green. Okay. Then in the second one, we're looking at blue versus all. So let's say if I look at blue versus all, this is going to be the separating hyperplane, and I'm going to call it f hat blue. And finally, for the third one, if you look at red versus all, so maybe something like this is going to be my f hat of red. Okay, so that's step number one. Fit 3 different 2-class SVM classifiers, call them f hat green, blue, red, and this is defined by going over each class versus the rest. Step number 2, classify the test observation to the class for which the f hat of k in that for that observation is largest. So by largest we mean that it has the largest positive value, right? And we know what do we mean by value. So for example, we have +3, -2.5, and etc. Right? So let's do an exercise. So imagine we have these 3 f hats, f hat green, blue, red, and I'm interested to classify. Let's say, let me use another color. Let's say I'm interested to classify this observation, right? This purple observation here. This is my X in the test set. Well, ex ante, we know that if we visually look at that, we know the answer should be class red, right? But let's see how does the one versus all is going to help us to classify this, right? So we already have the hyperplanes, f hat green, blue, red. So let me write them down here. So f hat green, then f hat blue, and then f hat red, right? And now let's calculate f hat green for the x in the test set, f hat blue for the x in the test set, and f hat red for the x in the test set, right? So what do you think this number should be? Look at that. I want you to focus on f hat green first, and then look at the test set and tell me, what do you get? Is it a positive number, negative number, and what? Let me actually help you out by drawing this hyperplane one more time here. So well, I think it's something like, I don't know, maybe something like this. This is for f hat green. This is our f hat blue. And this is our f hat red. Okay, so let's see. Actually, on purpose, I tried to put the test sets right on the green hyperplane. Okay, so let's start with f hat red, right? So what is f hat red for this test observation? What do you think is the number? So first of all, we're looking at the perpendicular distance from the red hyperplane, right? So basically the perpendicular distance of this observation from the red. So let's say in terms of magnitude is equal to 2. What is the sign? Positive, right? Positive 2, because X test set is on the correct side of the red hyperplane. Okay. So what about the blue one? So the perpendicular distance of this observation from the blue hyperplane is a larger number. Let's say it's 4, but what about the sign? It's on the wrong side of the hyperplane, so it's -4. Okay, and then finally, let's look at the green hyperplane. So this X test set, the purple one, is exactly lying on the hyperplane. So what is the f hat for that? Yes, the f hat is going to be 0, right? Because the distance is 0, right? So we have 3 numbers, 0, -4, and +2. What is the largest one? The largest one is going to be +2. So the model is going to classify this test observation to be class red. This is what we suspected from the beginning, right? So this is how the SVM is basically the model OVA, one versus all, is helping us to classify multiple class classification. The next method is called OVO, or one versus one. So the idea of OVO is very simple. We have already covered one versus all. Now let's talk about one versus one. So let's go over the steps. We're going to fit all of the pairwise classifiers. So if I have 3 classes, we're going to have 2 out of 3 combinations. Basically 3 combinations of between 3 classes, right? So let's look at this example. We have green, yellow, and purple. So we are comparing green versus yellow. We are comparing purple versus yellow, and then we can compare green versus purple, right? And then we're going to report f hat of k and L is the one that we're going to compare it with, right? Each class versus the rest, versus the other one, actually, the other pair. Then we are going to classify the test set, the X observation in the test set, to the class that wins the most of the pairwise competition. Okay, so let's how it's done in practice. I'm going to go ahead and define f hat of green and yellow, f hat of green and purple, and f hat of yellow and purple, right? And then let's say I have a test observation here. Okay, if this is my test observation, the model better to classify it as purple, right? Because we already know that the answer should be purple. But let's see how it's doing the job in action. So starting with the first one, so let me write down this observation here. Okay, so between green and yellow, so let me highlight it using the red. So between green and yellow, this is going to be our classifier. Okay, so between these 2 classes, which one is the winner? Green. Very good. The next one is between green and purple. So between green and purple, what is the hyperplane? This is a green and purple hyperplane. So which one is the winner? Yes, purple. And then finally, between yellow and purple, so basically this hyperplane, which one is the winner? Purple. So what is the majority vote? What class wins the most pairwise competition? Purple. So the answer is going to be, the model is going to classify this test observation to be purple. Okay, now just to make sure that we have understand how this one versus one work, let me give you an exercise. So can you classify this observation? I want you to pause the video and then fill in the blanks here. Hopefully you are able to identify it as yellow class, right? So let's go over it step by step. So f hat of green versus yellow, right? So we are starting with green and yellow. So this is this hyperplane. So the winning class is going to be yellow. The next one, green versus purple. So this is our green-purple hyperplane. The winner is going to be green. And finally, yellow versus purple. Actually, this is going to be the hyperplane, and the winner is going to be yellow. Again, the majority vote is going to be yellow, so the model is going to classify this observation as yellow. Okay. All right, now that we know what is OVA and OVO, which one is going to perform better? Okay. So in the literature, the consensus is that most of the time, one versus one is going to perform better. Okay, but we have to pay attention that it all depends on the number of classes that you're classifying. If it is 2 class, 3 class, well, for 2 class, we don't need to deal with it, right? But if it is 3 class, 4 class, that's fine, because the number of 1 versus 1 is going to be very close to 1 versus all. However, if it is 10 class, the number of the 1 versus 1 is going to be a lot more compared to 1 versus all. So let me give you an example. Imagine we have 3 class, k is equal to 3. If k is equal to 3, for 1 versus all, we have 3 different combinations, right? So let's say class 1 versus rest, class 2 versus rest, class 3 versus the other all. For 1 versus 1, if k is equal to 3, again, we're going to have 2 out of 3 combination, pairwise combinations, so 3. 1 and 2, 1 and 3, 2 and 3, right? But what if k is equal to 10? If k is equal to 10, for 1 versus all, we're going to consider 10 different scenarios, right? Class 1 versus rest, class 2 versus rest, and etc. But for 1 versus 1, we have to do 2 out of 10 combinations, right? So basically, 10 multiplied 9 divided by 2, we're looking at 45 different pairwise comparison between the classes, right? So, and now you can guess if if the data set is large and we have to look at 45 pairwise comparison, this is going to take longer and it's not going to necessarily do a better job, right? But as I said, in the literature, the consensus is that most of the time OVO is going to perform better. Now let's talk about SVM pros and cons, starting with the advantages. Pros. SVM can be memory efficient. This means that it uses only a subset of the training data. It uses only the support vectors, right? But remember, this is after the model has been trained. So for the training process, the entire data set is used. But after the model is trained, only the support vector is going to be used when we are doing the predictions, right? So in that sense, it is memory efficient. At least compared to KNN, it's a lot more memory efficient. It can handle nonlinear data sets, and we know that the trick is kernel. So if you have a kernel and SVM, then it can easily handle the nonlinearity in the data set. Okay. It can handle high dimensional spaces, especially when the number of dimension is even larger than the number of observations, right? And the RBF kernel is going to be very powerful in terms of sending the coefficients of many of the features towards 0. And by that, it's somehow reducing the dimensionality of the data as well, right? And it is used both for classification and regression. And SVMs are not very sensitive to overfitting, especially if you're using the kernel trick. And we can think of the concept of soft margin and regularization, right? We can always tune the hyperparameter to make sure that the model is avoiding overfitting. And it can have high accuracy, and this is true even compared to neural networks. Actually, traditionally, the support vector machines used to be applied even for image recognition. But we know that now with the help of the computation power, we can easily use the neural networks, and neural networks actually has replaced SVM for image recognition. But still, SVM has very interesting and huge applications in economics and finance that we're going to talk about in the next slide. All right, so what are the disadvantages? So I think one of the biggest disadvantages of SVM is that by construction, it's a non-probability outcome, right? So non-probabilistic model. It gives you no probability. It's not like logistic regression or even KNN that we ended up coming with a probability for each class, right? For each observation. So this is a big disadvantage. And the next one is long training time when we have a large data set, right? So generally speaking, the SVMs are not fast enough when we are dealing with large data set, and they're designed for small to medium-sized data sets. Then the limited interpretability, this is another disadvantage, especially for kernel SVM. So maybe for a linear SVM, for regression, we can easily interpret that. But when it comes to the kernel SVM, we're kind of lost in terms of what are the weights for the coefficients, right? So we don't get interpretability for that. And then it does not perform well with the noisy data. And finally, it is suited to the small to medium-sized data set, right? However, for small to medium data sets with very large dimension, let's say thousands of dimensions in the data, SVMs are doing a very good job compared to other machine learning models. Let's wrap up this episode by going over SVM's applications in finance. So SVM has many applications in investment management. It is particularly used for small to medium-sized but complex high-dimensional datasets, such as corporate financial statements or bankruptcy database. Well, SVM is also used for identifying stressed company to short sell, basically using many fundamentals and technical features, right? Investors seek to predict company failures for identifying stocks to avoid or to short sell them. And SVM can generate a binary classification using many fundamental and technical features, right? So the next application is sentiment analysis. We know that SVMs can handle very high dimensional data, and they're powerful in classifying text from documents, right? For example, news articles, company announcements, and company annual reports into useful categories for investors, right? So even though today its neural networks has some sort of completely replaced SVMs because they're more powerful, but SVMs used to be applied for this kind of analysis as well, sentiment analysis. Other applications of SVM in finance is just basically like any other classification method that we have covered so far is examples like money laundering analysis and spam detection. Wherever you're thinking of classifying, things into two classes or more than two classes, you can think of SVM as a powerful method. And then finally, we can also apply SVM to loan management and basically decide we should, as a lending company, should you lend to a person with some specific app features or not, right? So, but in general, I want you to think of SVM application to the data sets that are medium to small size, but they're complex. The dimensionality is very large. All right, so that was pretty much it, and this is the end of our long journey in SVM, support vector machines algorithm in machine learning. Until the next video, take care.